So what we want to do is, first of all, typically a linear system will come to us wearing one of two disguises. It most often comes to us as a question about a system of linear equations that we're trying to find solutions to. But occasionally, it might come to us as a vector equation. This is a version that we didn't spend much time yet talking about, but once we get into the next chapter, chapter V, this is going to be big business. So when you look in your activity sheet, this example, activity 134, I did out for you. So I do encourage you to take a look at that at some point during the week this week. But I want us to focus for the remainder of our energy today on this activity. So we're given a system of two linear equations in the three unknowns, x1, x2, and x3. And we want to find its solution set. So there are two activities in a row that kind of address this question. And the way we're going to do that is first by converting this into an augmented matrix, and then finding a reduced row echelon form for that augmented matrix. Again, using technology. If you're feeling particularly spry, you can also try it by hand, but it's up to you. And then see if you can, by looking at the reduced row echelon form and probably changing it back into equations form, see if you can figure out what it tells you about how many solutions this linear system has. Is it consistent or inconsistent? So does it have any solution at all, or does it have no solution? And if it is consistent, does it have a unique solution, just one, or are there infinitely many solutions? See if you can figure out how the reduced row echelon form tells you that. And then I'll say, let's have you go directly then onto the next activity, which picks up on it. And it actually uses the reduced row echelon form from the previous problem. So a little bit of a spoiler here. But what it does is then it invites you to go through the work of figuring out how to write that solution set by assigning meaningless parameters to one or the other of one of the variables. And in this example, it actually asks you to do that in two different ways and see if you can quantify which one of them was easier. So I want us to come away from this last pair of activities, which you'll do in sequence, with two things. First of all, some practice converting between equation form and augmented matrix form, back and forth, so that we have practice with that. And then getting information out of the reduced row echelon form of a matrix. And then the process of doing the end game process, the thing that we started today with by recalling from the first day's activities, by writing the solution set, by assigning a meaningless parameter to one of the variables. And then we'll have a closing discussion where we'll talk about how can we choose, how do we make the choice for which variable we should assign the meaningless parameter to. So 1.3.5, 1.3.6. I double checked, and both of these are the same on my screen now as they are in your activity file. So we should be all good to go with these two. So if you're using the Sage cells that are part of the textbook, they use a special language in Sage called Octave that is a little bit more streamlined than the full Sage language that I was putting on display before. And so for that, if you want to find the reduced row echelon form of a matrix, just zoom in on this a little bit so we can see it better. You'll just type the entries of your matrix in square brackets with commas in between them and a semicolon at the end of each row. So in this example, our augmented matrix is 1, 2, 3, 1. And at the end of that row, put a semicolon, 2, 4, 8, 0. Put that in square brackets and then surround it with parentheses and REF in the front. And so when you do that evaluation, it spits out the reduced row echelon form for that matrix. And so the main goal of these two activities is not to find this REF, it's to interpret what this REF is actually able to tell us. So maybe let's quickly check in on if you answered part B. How did you answer part B? So how can we understand at this point how many solutions this linear system is going to have? Before we're able to put this on a firmer foundation, we might say, well, there's three variables, but there's only two equations that bind them. And so this is an example of a system that's sometimes called underdetermined. There aren't enough equations. There aren't enough relationships between the variables to give a unique single solution to this system. And so we probably expect that if this is a consistent system at all, then the number of solutions is going to be infinitely many. Remember, those are the only three possibilities for how many solutions a system has. None if it's inconsistent, or if it's consistent, it either has one solution and only one, or it has an infinitude of solutions. One solution for each real number that we could pick for whatever are its free parameters in it. So we don't know for sure that it's the case yet, that this particular system has infinitely many solutions, but that's the purpose of the final activity of the day. And that is to take the RREF that we found in the previous problem, convert it back into equations. So what we're seeing in these equations is sort of the simplest possible expression of the relationship among x1, x2, and x3 that has disentangled the variables from one another to the greatest extent possible. Now we want to use that expression, right, this simplest possible version of the equations, to come up with solution sets. And in parts A and B, respectively, you're going to assign a free parameter, meaningless free parameter, to either x1 or to x2, and then write in vector form what your solutions end up looking like. And then finally, kind of assess, like, why was one of these a little bit easier? Why did one of these give you a little bit less work to do than the other? So that's going to be how we finish up. So I want to give maybe 5 or so minutes just to work on that. There's almost no computation left, just to do this variable assignment and then solve for each one of x1, x2, and x3 in terms of that meaningless parameter. And then just talk about which one was easier and why do you think it was easier. All right, so the very last activity for today had you using the reduced row echelon form of this system that we looked at in the previous activity, right? And this was the RREF 1, 2, 0, 4, 0, 0, 1, minus 1. And turning that reduced row echelon form back into equations, that again is the step where when student solutions to linear systems go off the rails, it's usually because they forget to do that step, because they're often in a rush to do the steps that come next. And those are the steps we're doing in this activity, which is to take either the variable x1 or x2 and replace it with a meaningless free parameter, and then use that meaningless free parameter to express the other variables in terms of it. So if I replace x1 with a free parameter a, then I can solve the resulting equations for x1, x2, and x3. x1 is equal to a, x3 is equal to -1, so it doesn't depend on a at all. But x2 is then going to be equal to 4 minus a all divided by 2, just from solving this first equation for x2 after replacing x1 by that free parameter a. And so that's one way of expressing this solution set. On the other hand, if I chose x2 to be my meaningless free parameter and replaced it with a b, then solving the first equation for x1 gives me 4 minus 2b. And so I get a slightly different expression for the solution set. Now, notably, we're describing the same solution set in both cases over here, right? Both of these are valid descriptions for the solution set of this linear system. And it's worth kind of thinking about why, like how we know that these two sets are exactly the same. I make a lot of backhanded references to linear algebra during my multivariable calculus class, but this is a time when I'm going to make a back reference. So if you're taking multivariable calculus with me this summer, you'll recognize these solution sets as being parametric equations for a line in three-dimensional space. And so you could figure out what's the direction vector for these lines, and how do I know that these lines are the same line as one another. We know that along these lines, all of the z coordinates, of the x3 coordinates of all of our points are equal to -1, but then it's a valid question to say, how do I know that the other directions describe the same thing? But anyway, that's for my multivariable calculus students' pleasure. So the question that we want to end with, coming to an answer to, is how could we have known, what features about this reduced row echelon form should have told me that I get to make a free choice of a parameter? So the prediction that this group made about how many solutions this system had, it's probably got infinitely many solutions because it's underdetermined. There aren't enough equations to give all three variables a unique value. And it turns out that that is a correct response, because I know there's infinitely many solutions anytime I have a free parameter. Because as soon as I have a free parameter, I have infinitely many different real numbers that I could choose for that real parameter, right? And that means that I have infinitely many solutions as part of my solution set. So how could we have known that there is a free parameter available to us in this? What was it about the reduced row echelon form, do you think, that should have indicated to us that there is exactly one free parameter that we can choose? And as soon as I choose that one free parameter, it can determine the values of all the other variables. So what do you think it is about that RREF that should have been a clue?
The column, sorry.
It's the column without any pivots. So when I look at this reduced row echelon form, the first column corresponds to the x1 variable, right? It has a pivot in it, in this top left position. So does the third column. So the x3 column has a pivot in it. And so what that's telling me is that the values of x1 and x3, we don't get to make a free choice of. But the column without a pivot, the x2 column, is telling me that that variable x2 can be chosen freely. And if I choose x2 freely, then that choice can determine x1 and x3. So that's the sort of the big takeaway from this exercise, which answers a question that was asked at really the beginning of our class. I think it was Peter that asked, well, how do we know which variable we can choose to be our free parameter? And the answer is whatever variable corresponds to a non-pivot column. Just based on the definition of pivot, no column can have more than one pivot, no row can have more than one pivot. And as a result of that, it's because we can't have a pivot that's to the left of any of the pivots that are above it. Every pivot has to be to the right of the pivots that lie above it. So we can't have more than one pivot in a row. We can't have more than one pivot in a column. And so whichever is the lesser number of my number of rows and number of columns, that's going to constrain how many pivots I can have in my system. So I had 3 variables, but only 2 equations. So my augmented matrix had only 2 rows, which means I could not have possibly had more than 2 pivots in my system. And because I have 3 variables to choose from, and I can have at most 2 pivots, that means at least one of those variables has to be a free parameter, a free variable at the end of the day. And so that's going to guarantee infinitely many solutions. So that's the more sort of linear algebraic answer to the question, how do we know that an underdetermined system like this one is going to have infinitely many solutions? When it's consistent, I should specify, when it's consistent, it will have infinitely many solutions. And we know that because it will always have a free parameter, at least one of them, because it can't possibly have enough pivots to make every one of its variables in a pivot column. So notice, though, that we could also have chosen x1 to be our pivot and used it to determine x2. It's just not what the method would have sort of selected for us in the process, right? The part B choice, where we made our x2 the free parameter, was a little bit easier. And the reason it's a little bit easier is we didn't have to do any division. And the reason that we didn't have to do any division is because this x1 variable is one of the pivots, and so its coefficient was 1. Right? So that's another reason why we love to have 1s in those pivot positions, is that then when we express the bound variables, the pivot variables, in terms of the free variables, we don't have to do any division in the process. And so we don't end up with any nasty fractions. As long as all of the entries in our RREF are whole numbers, then all of the entries in our solution set can be expressed as whole numbers. And so all the coefficients of our free parameters end up being whole numbers. So the path of least resistance is to let your non-pivot column tell you, or columns if there's more than one, tell you which variables to make your free parameters. And then once you set those variables as your free parameters, you can solve for the other variables in terms of them and come up with a solution set expression like this one. So your work for the week is going to be quiz 2, which is going to ask you to do one of each of these things. So do out a row operation problem once and for all. Right? After that, you can use technology. And then in the solution sets type problems, it's going to be very similar to the last activity that we did here, where you're given a linear system, either in its equation form or in its vector form. Turn it into an augmented matrix, use the reduced row echelon form of that augmented matrix to then go back into equation form, assign your free variables meaningless parameters, solve for the bound variables in terms of those parameters, and then you have a description for your solution set in its vector form.